This is also a formula which will be used immensely in this exercise. So e raise ax cos bx is equal to what you see on the right, and I'm going to prove it just now. So we have already proved e raise ax sin bx. Now we are dealing with e raise ax cos bx. So you are always told that I late you can follow. Okay, inverse, log, algebraic, trigonometry and exponential. So you can follow this, or you can take any of these as the first function and second function, because in the previous discussion just now I have taken otherwise. But here you can take in a different way, because this particular integral doesn't follow this I late. Means either of the function can be taken as the first function and second function. Actually I have tried out, that's why I am telling you. You'll see it just now also. And you will see the difference between e raise ax sin bx and e raise ax cos bx. The previous one I took different first and second function. Here I am taking different first function, second function. So I is actually e raise ax cos bx, which we are integrating, and I am writing it again just to show you that this is going to come again. This will be regenerated while we are actually solving the question. Now let's apply the formula. This I will be equal to, so integration of uv dx, I told you already in the previous one, so I am going to just apply the formula here. So this is cos bx as the first function, integration of e raise ax, and then the differentiation of the cos bx first function, and then integration of e raise ax, and then with the dx. So we have cos bx, integration of e raise ax will be e raise ax, and then the differentiation of ax will give you a, and that will be kept in the denominator. So you have a in the denominator, minus. Now cos bx will be what? It will be negative sin bx. Remember, you are differentiating here. So minus minus, I am making it plus here itself. So minus sin bx, cos bx will be negative sin bx, and then bx will also be differentiated. That will give you b. And what about integration of ax? It will be e raise ax by a. So we need to integrate it again. Let me add b also. So this has to be integrated again because it is inside an integral sign. We have e raise ax sin bx. I have taken b by a outside. So let me just compete by writing this e raise ax divided by a, and this is cos bx, I equal to this one. Now let me call this as I1 because I am going to do it separately just to increase the understanding. E raise ax sin bx on the right, I have taken it as I1 at my disposal. So again, you can take any of this as the first function, any of this as the second function. You don't need to follow I late. So I'm taking sin bx as the first function and e raise ax as the second function. So let's start with sin bx now. This is sin bx, integration of e raise x minus integration, then the differentiation of sin bx will give you cos bx, and then since differentiation has been done, b will also come. Integration of e raise x also. So we have sin bx, this will be e raise ax by a minus this differentiation of cos bx has already sin bx has already been done, so we have a b cos bx. So there will be b cos bx. I have left it, just assume that it is there. E raise ax will be e raise x by a. So let me write b also and cos bx also. So cos bx here. Now to our again a surprise, you'll see that from where we have started, we have again come back to the same juncture. That is the first term I am writing like that. But here if you take b by a outside, the inside will be e raise ax cos bx. And what is this? I told you that it is going to be regenerated. It will come again. So this is I only. So let me substitute this as I only. That is e raise ax sin bx divided by a minus b by a. And this integration of e raise ax cos bx will be I. And there is a b by a also. So let's multiply b by a here only just to make it clear and not very clumsy. So b, I am multiplying now. So b e raise ax sin bx is the numerator, a into a is the denominator, a square. Now again b by a into b by a will be b square by a square with an I. Now I am taking this all and putting it in the original equation. So e raise ax cos bx by a will remain like that, plus b into e raise ax sin bx by a square. I am just taking this and putting it here. Nothing, no change I am making it here. Minus b square by a square I. Now this rightmost thing I am just taking or transferring it to the left hand side. So this will form I plus b square by a square into I equals to what? I 1 plus b square by a square if you take I common. So this will be a square plus b square by a square into I. So left hand side will be now a square plus b square by a square into I. And on the right hand side, e raise ax, let's take common. What will remain inside? Cos bx plus b sin bx. Here it will be a and here it will be a square. Now let's take the LCM. When you take the LCM, it will be a square. So since this already have a square in the denominator, you can just write b sin bx. Here we have only a in the denominator, so in order to make it a square, you have to multiply it with a cos bx. Okay, e raise ax remains here. Now a square plus b square by a square. First thing is you can just cancel this a square and s square in the denominator. And you can bring this a square plus b square on the right. So this integration I will be e raise ax, in the denominator it will be a square plus b square, and followed by a cos bx plus b sin bx. And now you can add a constant of integration, and this is actually the proof also and solution of the first question as well. This is from where we started, okay? So this is the proof of e raise ax and e raise x, cos x and cos bx and sin bx. Now just need to see it cleaner, and I want you to do it again.